Day 39, Honors Physics, Newton's Three Laws, Problem 48. This one here is a little bit of a challenge. In Part A, it's not stated explicitly, but it's highly implied that the block is almost ready to slide down the ramp. Although I'm going to do another extension of this where if the rope is pulling hard enough, it might be just about ready to go up the ramp. But it's implied that the rope is keeping it, just barely keeping it from sliding down the ramp. And then we're going to cut that rope, and then it will accelerate down the ramp. But there's the basic diagram. It's a good starting point. But let's draw all the forces on the block. So when we have this block sitting there, we have T right now up the ramp. Let me adjust that a little bit because there's two things keeping it from sliding down the ramp, in my opinion. There's the tension, but also friction acts up the ramp. If the block is about ready to slide down the ramp, you have static friction, I'll just call it F sub F, and it has a maximum value. So whenever F sub F is a maximum value, T is a minimum value. Because what's trying to pull it down the ramp is the weight vector parallel to the ramp. So we have W sub P parallel to the ramp. Then you have W sub N, the normal component of the weight, the perpendicular component of the weight. And you have F sub N, the normal force perpendicular to the surface. F sub N and W sub N will always be equal in these problems. Well, there are some exceptions, but we're not going to do any of those exceptions this year. So there's your full diagram with your components. Notice I didn't draw W. W would have been straight down, and we can do the computation for that. I'll do that over here. W is straight down, and you have your W sub N and your W sub P, as we always do. In this case, it's a 45, 45, 90 triangle, so you can take some shortcuts. That should say 45 degrees, 45 degrees. So W in this problem, since it's a 10 kilogram block, so W is 100 newtons. So W sub P, and if you want to take the shortcuts for this, as long as you have your little diagram there, you can use sines and cosines, or you can just use the rules for 45, 45, 90s. The legs will be the hypotenuse divided by root 2, which I believe it comes out to be 71 newtons if you divide by root 2. And they're equal because it's a 45, 45, 90 triangle. So I can start filling those numbers. In other words, in this diagram I have on the left over here, W sub P is 71 newtons. So this is 71 newtons. Wn is 71 newtons. F sub n is 71 newtons, only because, well, F sub n and W sub n are always equal, but W sub P and W sub n are equal because it's a 45, 45, 90 triangle. All right, now friction, the 71 newtons W sub P is what's trying to make it slide down the ramp, and that will be the accelerating, the main acceleration part of the net force in part B. But for now, we want to figure out the maximum frictional force, the maximum static, because right now it's not moving. F sub F max is when you put the equal sign into the static friction equation, equals mu. Does it tell us mu, static friction? Yeah, 0.4 times the normal force, which is 71 newtons. So our maximum frictional force that can keep this block from sliding down the ramp, and so just say MAX, the maximum is 28 newtons. So that's the best friction can do. So the tension, right now there's a 71 Newton force trying to pull it down the ramp. Let's put the 28 over here by friction. So the rope has to help out a little bit to keep it from sliding down at minimum. Because if you, well, let's just figure it out, because right now if this is at rest, which it's not accelerating, so if you look parallel to the ramp here, F net has to be equal to 0, or in other words, 71 minus 28, which is what, 43? The tension must be 43 newtons. So if let's just write that down. You can maybe see that when I write that down. This must be 43 newtons. That's the answer to part A. Because 43 plus 28 is 71 newtons. That will keep the block just barely restrained from slipping. However, for example, if you start pulling harder with your rope, if you have some control over your rope, if you pull harder, then friction doesn't have to do as much. So for example, if I pull with 51 newtons of force with my rope, then friction only has to be 20 newtons because friction can be less than its maximum value. So I can have a higher tension than 43. I can have 53, 63. I can have a 71. In fact, if I pull with 71 newtons of force on that rope, then friction wouldn't be necessary at all. Or conversely, if I continue to go with my pulling of the rope up the ramp, if I exceed 71 newtons, now that's trying to make the block go up the ramp, so friction would be down the ramp. So you would have a new situation here. So here's the bonus part of this before I go to part B. Let me draw a new diagram. If I pull hard enough such that the impending motion is up the ramp, the static frictional force will be down the ramp. So it would look like this. So up here in the black diagram, I have the scenario. Once again, if I pull with a tension of 71 newtons, we don't even need friction. Friction would be 0. Once I exceed 71, say I go to 80 newtons upward with my tension. If my tension was 80 newtons, then my force of friction would be 9 newtons to keep this all balanced, because static friction will match to keep the situation at an F net of 0. By the way, you can see here in this black diagram, I filled in all the actual numerical values for the components of weight and the normal force, because they're not going to change. But once again, if I look at this situation where I'm pulling harder and harder with T, such that I'm pulling harder than 71 newtons, the force of friction will maximize eventually at the same maximum value as it was before, 28 newtons. It can have a maximum of 28 newtons. All right? So now we'd have a sum of about 99 newtons down the ramp. So if I'm pulling with 99 newtons of force up the ramp, friction can still match that, kind of. We're at the tipping point right now, the break-even point, because there's two forces pulling down the ramp, 71 and 28. But if I pull harder than 99 newtons, just barely harder than 99 newtons, this thing will start to accelerate up the ramp, then we'd have a kinetic situation up the ramp. So what I'm saying is this: the tension in the rope actually can be anywhere, well, it's stationary, anywhere between a 43 Newton force down here over in this first diagram up to 99 Newtons. Anywhere in there, the block will stay stationary. If you pull harder than that, it will start to accelerate up the ramp. If you pull less than that, the block will accelerate down the ramp. And now, if you cut that string, like in part B, that tension force disappears altogether. So let me draw that. So the situation simplifies a fair amount once you cut that string, and the mass will certainly, or the block will certainly accelerate down the ramp now once you cut the string, so the force of friction will indeed be up the ramp, and now it's kinetic friction, so we need to recalculate that. There is no less than, more than, greater than, it's just force of friction, kinetic, is the coefficient, mu, 0.20, times the normal force of 71. And since that's half the coefficient of the static situation, you can check it with your calculator. Round it off to 2 sig figs, that's 14 newtons. So the kinetic friction will be 14 newtons no matter what. There is no less than, more than. So as it's sliding down the ramp now, that frictional force will maintain, and we can just apply F net equals ma. So let me change colors. F net equals ma. And looking at the diagram, the big force causing the acceleration, well, the bigger force is the 71. So we have 71 minus the force of friction opposing it, 14. Together that would give us F net equals the mass, which was 10 kilograms, times A. Solve for A. And you have the acceleration down the ramp.